You might have heard things like how whale calls are at a lower pitch and frequency because they are more effective underwater. Have you ever wondered why? Have you ever noticed in movies why people touch their hands down on a track to see if a train is coming? You might be saying, well, duh, obviously, they're going to feel the train coming before they hear it coming. But why would the sound of it coming through the air take longer than the vibrations coming from the track? In this video, we will be trying to understand why this happens, but also focusing and analyzing how sound waves travel through different liquids and mediums. First off, let's start with what sound is. Personally, before I started this project, I knew sound was a vibration created from particles hitting each other, and the only reason we hear them is because our eardrums would quote-unquote catch those vibrations. After refreshing my wave knowledge from grade 11 and doing some extra research, I have a more concrete understanding on what sound is. Sound is a longitudinal wave, meaning the vibration or movement of the particles in the medium is in the same direction as the wave is traveling. Let's focus on the particles in the medium. Medium, meaning what is surrounding the particles. This could be air, water, or even a solid. No medium equals no sound. There'd be nothing for sound to travel through. Okay, now that we know what sound is, let's try answering the previous questions through my experiment. Here's my process. I took an empty container, measured its volume, recorded the mass of the empty container, and then filled it with purified water and found the mass of the water. Boom, I found my density. You may be wondering, why do you need density? What is your experiment even about? Well, here's your answer. This formula. Velocity equals root of K over rho. Rho meaning the density of your fluid, and K the bulk modulus. Let's start first with what confused me the most. What does bulk modulus even mean? Well, in simpler terms, the bulk modulus is how resistant a liquid is to being compressed when pressure is applied. The bulk modulus can be found by using the formula K equals negative change in pressure. The negative sign is because an increase in pressure usually leads to a decrease in volume, over the change in volume over the original volume. This is because the more resistant a material is to changing its volume, a smaller fractional change, the higher its bulk modulus, because it's harder to compress. Makes sense. Okay, now why is K over rho rooted? Well, if you look at the units, K equals newtons per meter squared, and rho is kg per meters cubed, its volume. K over rho gives you meters squared over seconds squared. You just need to root it to get meters per second, aka your velocity. Now, let's focus on the first experiment, purified water. Why purified water? Well, using tap water would work. It just means the impurities in the water could affect my results. I think of it like having more stuff in the water that makes it harder to compress, aka a higher bulk modulus. For my experiment, on one end of the container, I had an underwater speaker, and on the other, I had an Adeline AD35 mini piezo pickup contact microphone transducer to pick up the vibrations. My initial plan was to use time delay analysis to measure the time taken for sound to travel across the container. Easy, right? Too bad the largest container I had was 67 centimeters long. And this is what stumped me for a while. How in the world am I meant to find velocity without knowing how long it takes for the wave to travel from one side of the container to the other? In order to do that, I would need a stopwatch that could record microseconds and the reaction time of a god. Earlier I was talking about another way to solve for velocity. I literally explained how velocity equals root of K over rho. All I needed was the K value. And wouldn't you know it, the engineering toolbox has everything I need, in imperial units and SI units. Okay, let's plug these values in. Water has a K value of 2.09 times 10 to the 9 PA newtons per meter squared. Velocity equals root 2.09 times 10 to the 9 over 995 kg per meters cubed. Our velocity is 1,449 meters a second. Sounds about right. Let's make sure the value we're getting makes sense by comparing it with the speed of sound in air from its bulk modulus and density. Density of air, 1.204 kg per meters cubed, much lower than water, which makes sense. For gases, the bulk modulus is equal to the pressure if the process has a constant temperature. Why does this make sense? In gases, volume changes easily because gas particles are far apart and can be compressed significantly. The pressure inside the gas itself is the force per area pushing outward, resisting compression. So when you try to compress a gas a little, the pressure inside increases nearly proportionally to how much you reduce the volume. This relationship is described by gas laws, like Boyle's law, which shows pressure and volume changes are tightly linked. Let's assume atmospheric pressure and now solve for velocity. V equals 101,325 over 1.204 all rooted. Our velocity is 290 meters per second. Would you look at that? Our calculations say that the speed of sound in water is much faster compared to in air. Did I do something wrong? Well, let's check two more times, once with salt water and once with glycerin. Salt water has a higher bulk modulus of 2.3 times 10 to the 9. Makes sense, harder to compress than normal water. Higher density also makes sense because there's salt along with water. Velocity equals 1498 meters per second, slightly faster than in water without salt. Glycerin has a density of 1260 kg per meters cubed and a bulk modulus of 4.35 times 10 to the 9. Notice how the bulk modulus is double water. The velocity we get is 4.35 times 10 to the 9 over 1260 all rooted, which is 1,858 meters per second. Notice the trend? The more dense a liquid, the higher velocity. Remember how before, an example I used was a person touching their hand to a train track to feel if a train was coming? That's because sound travels much faster through solids like steel than through air. Even though steel is extremely dense, its stiffness is so high that it allows vibrations to travel very quickly. The same principle applies with liquids. Okay, let's pause now. We know that vibrations travel through mediums with higher densities much faster because the tightly packed particles can pass the vibration on much quicker than if the particles were spread out. Now let's go to a real-world application. After going through this experiment and my understanding so far, you may be wondering, if sound can travel through everything, even walls, why am I not hearing every single vibration going on in my home? Well, that's where things like impedance, refraction, and absorption come in. Every material has what's called an acoustic impedance, which is basically how much it resists the movement of sound waves. When sound tries to pass from one material to another, like from air to a wall, if there's a big difference in impedance between the two, most of the sound reflects back instead of passing through. That's why you don't hear your neighbors clearly through a wall. Then there's refraction. As sound moves from one material to another, especially at an angle, it can bend or change direction. For example, underwater, sound can bend due to temperature or pressure differences. This is why submarines can hide beneath certain layers in the ocean where sonar waves bend away from them. And finally, absorption happens when part of the sound wave's energy is lost as heat inside the material it's passing through. Soft materials like carpets or curtains absorb more sound. That's why rooms like rugs and furniture feel quieter. Those materials soak up the vibrations instead of letting them bounce around. So even though sound can travel through many materials, how much of it reaches your ear depends on how much is reflected, bent, or absorbed along the way. That's why understanding how sounds travel through different mediums, like I explored with water, salt water, and glycerin, is so important, not just in physics projects, but in designing buildings, sonar systems, and even understanding how animals like whales communicate. Thank you for watching.